All right, in this work example, we'll be looking at some electric circuit questions. So this is question number 6 that comes from ACE Physics Syllabus Code 9702, paper 23, that was administered in May, June of 2018. A wire X has a constant resistance per unit length of 3 ohms per meter. So it's kind of like every meter you go down this wire X, there's 3 ohms of resistance. So it's telling us how much resistance it has per unit length. And it tells us the diameter of this wire X. Calculate the resistivity of the metal. Here, if you don't have an equation in mind for resistivity, you'd be completely stumped and you just have to kind of give up on it. So if you don't know that resistivity rho is equal to resistance times cross-sectional area divided by length, you're stuck, right? So like if you didn't make it this far, you probably didn't earn any marks. But if you at least knew the right equation, but maybe you didn't know from there how to go about it, you know, then you might have got 1 out of 3 for maybe just sort of writing this. All right, let's see what else we can do. So we're solving for this. It's kind of interesting the way that they've presented this data, because it almost seems like this isn't enough to solve it, but they're telling us really the value of R per L, right? They're saying, hey, per unit length, which is what's in the denominator, like per length, that's the resistance. And so this value here is this, right? Like 3 ohms is the resistance per meter of length. And so they've already taken the ratio for us. They've just sort of given us R per L. That's kind of nice and good units too. But the diameter is the tricky thing about this, because the diameter is not the area. You can't just substitute that in for area, right? So let's think about what is the area, the cross-sectional area of a cylindrical wire, right? This wire here looks like a cylinder with circular cross-section. So the area of a circle is pi r squared, where that right there is r, the radius of the circle. We're given the diameter. So we know the total diameter is 0.48. I'm going to change milli to 10 to the negative 3 meters. So that's the diameter D. What I need to substitute in for the area is half of that, okay, for R, and then squared, and then times pi. So I think I'm good to make some substitutions here. Rho equals, the thing I want to solve for, R per L, we said was given, so it's just 3 ohms per, I'm just gonna put 1 meter, makes it a little bit more clear to me that like, oh, my L is like 3 ohms per this many meters. Maybe I don't have 1 meter, but I know for each meter, this is the resistance across its unit length. And then the area here is going to be, all right, so I'm gonna take half of this, because I know this is the diameter, so I want half. So I'm gonna go 0.24. All right, I'm just going to do that in my head. 0.24 by 10 to the negative 3. That's R now, right? If this is D, then R is just going to be 0.24 by 10 to the negative 3 meters, millimeters. So there's R squared, and there's pi, right? Pi r squared. That's the area A. A is pi r squared. So just take care of everything. That's like, okay, we know how radius relates to diameter. Half of it. Crunching some numbers now. 3 times, actually, I'm gonna start here. 0.24 times 10 to the negative 3 is the same thing as 2.4 by 10 to the negative 4, right? You can move that decimal point over. I'm gonna square that in my calculator and then multiply it by 3. And then multiply it by pi. I get 5.4 by 10 to the negative 7. If you were able to calculate that in the lengthy class time that I gave you to sort of think through this, that's really good. That's awesome. If you didn't get that, but you kind of, you know, you did your best and you set it up and now you see your mistake and you're like, oh, I didn't half the diameter. I forgot the milli is 10 to the negative 3. It's so worthwhile to give yourself feedback and say, where do I need to sort of remediate my learning? I need to focus on the metric prefixes. I need to remember to square things. I got to take care of the transfer errors. I lost pi, you know, somewhere along the way. It's a shame when we lose pi, right? I don't want to do that. And then the second part of this, you know, you faced, here was calculating the potential difference across R. So let's get rid of all that. And now let's consider what we've got here. Everything that's sort of written out here is sort of included on the figure. There's our wire X. And again, we know like it's got 3 ohms per unit length across it of resistance, but they're asking us the potential difference across resistor R. If we knew the potential difference across here, the terminal ends of our battery, then we could say in a parallel circuit, voltage is the same across parallel branches. So we have like wire X is on a branch. In other words, there's a loop right there. And then resistor R is on sort of an outside loop. So these are in parallel with each other. The same voltage across this will be across here, will be across here. We can't simply say, oh, 5 volts. That's the EMF. And so there's 5 volts across here and here, because we do have the added complication that we introduced yesterday with our lab work, internal resistance, which means the potential difference across the terminal of the battery, V, which is the answer to this question, is equal to the EMF, which is given 5, minus those lost volts. Forget about the lost volts, okay? They're already lost, we don't want to forget them too. And so here we can say that the potential difference at the terminal of the battery, V, is equal to the 5 volts of EMF minus the 1.6 amps of current that are being driven through this EMF source that has itself 2 ohms of internal resistance. In other words, we know that there's 1.6 amps getting here, some of it going through here, some of it going through here, but they all meet back up here per Kirchoff's first law, which says that the sum of the currents going into a point come out of it. And so here the currents sort of diverge. Some goes this way, some goes this way, but they all meet back up over here, right? They have to sort of go out this way. They meet back up over here. And so we have all 1.6 amps of current going back through the battery, being driven through the battery with an internal resistance lowercase r equal to 2 ohms. And therefore we're going to lose 2 times 1.6 or 3.2 volts. And so the 5 volts of EMF minus the 3.2 lost volts means the terminal PD is only 1.8 volts. And so there'd be 1.8 volts. If we were to put a voltmeter across here, it should read 1.8 volts, right? Because as we drive that much current through the battery, we're losing, more than half of our volts there. So 1.8 volts for the potential difference across R. Now, the rest of these calculations we'll kind of do on the fly here. We'll think through them together because unless you queued up the paper and sort of worked on it independently, I only published those first 2 calculations. But the remainder of this paper is, or this question on this paper is, determine for wire X, the resistance, and its length. Do that, but maybe that would help. All right, so we want the resistance and the length for wire X. And remember, wire X was the one that we sort of dealt with up here. So we know everything is true about it, here. But we also have some clues maybe now that it's in our circuit, right? The resistance and the length of wire X. All right. Let's clear all that off. Let's remember that if there's 1.8 volts across here, there's also 1.8 volts dropping across here, right? That was the total sort of terminal PD. Our job is to determine the resistance of this. So what is the resistance of this wire X? And then its length. And I think if we have the resistance, the length should be really forthcoming because we already know that R per L is 3. So if we can figure out, the resistance of this thing, we'll just plug that number in here, and then we can solve for L because we already know the ratio of its resistance to its unit length is 3. All right. How do we figure out R? R equals V over I, Ohm's law. We know the voltage across this is 1.8 volts, but we don't know the current that's going through here. Okay, so we can't solve this yet. What we do know is Kirchoff's first law. The sum of the currents going into a point is the currents coming out of it. some of the current's coming out. So some of the 1.6 amps is going this way. If we can conclude how many of the 1.6 amps is going through this one, then bingo, all the rest have to be going through here. It's a fun puzzle that we get to solve together. You guys are so lucky. You know, I never got to have this much fun when I was in high school. All right, so how are we going to figure out the current here? Let's go. I equals V over R. We know there's 1.8 volts, right? We just figured that out. Okay, we know the resistance of this one, 4.5 ohms. And now you're starting to realize it is a fun puzzle that we get to solve. This is awesome. The current through here, 0.4 amps. See how the thing just breaks itself wide open. If we know there's 1.6 amps going into this node, and I can deduce from my Ohm's law of physics that 0.4 amps are going this way. So that means I got 1.2 amps going that way. Does everybody follow that? That is to say, let me do it very formally. The sum of the currents in equals the sum of the currents out. That's Kirchoff's first law. The sum of the currents into this node is 1.6 amps. The sum of the currents out is 0.4 amps, right? That we got here from, you know, Ohm's law, plus something, the current that's going through wire X. And that's how we can deduce by subtracting 0.4 from both sides. You start saying, well, that's not too bad. I can do that in my head. 1.2 amps going this way. Now we've got R here is still equal to V over I on this branch. Parallel branch has the same voltage, 1.8 volts that we already calculated, the terminal PD from our terminal PD equals EMF minus lost volts equation divided by the newly discovered current going through this branch, 1.2 amps. And we can deduce that the resistance of wire X is the ratio 1.8 divided by 1.2, or R equal to 1.5 ohms for that. And so if every meter gave me a resistance of 3, but this here wire is only 1.5 ohms, well, that's half of it. And so I can just kind of say, well, L is half a meter then. But feel free to just sort of do that very, again, formally. If we know that R over L is 3, and now we know that R is 1.5, we're saying, okay, multiply both sides by L, divide both sides by 3, 1.5 divided by 3. Indeed, L is a half a meter. Right? Because, you know, the numbers are so friendly there, that's maybe overkill, but it's important to sort of see the formal way to sort of set it up and solve it always works. If the resistance per meter is 3, we only have 1.5, then we don't even have all 3, you know, ohms. This thing would have to be twice as long to have a 3 ohm resistor there. It's only a 1.5 ohm resistor. As the charge goes through, the voltage is dropping uniformly across this wire. Remember what resistors are. They're just pieces of metal, right, that have certain resistivity, okay? They have a certain length and they have a certain cross-sectional area. And it's those 3 things that really govern what the resistance is. So that there again is your resistivity equation, but this time solving it for R. So we take a piece of wire and we wrap it all up and put it in a little, you know, plastic capsule, and there's a resistor, but this wire itself acts as a resistor, right? Stretched out like that. Let's go ahead now and share more of the screen, this much more. I'm going to change these letters P to MS for mark scheme, and that will immediately queue up the mark scheme for this paper because all the rest is the same. Clear that. And we were doing question number 6, I think. It should be clear once we get to it. Hey, that looks familiar. All right, let's give ourselves some feedback here. Again, I said, if you don't start with this equation, you kind of stumped. Do we get 5.4 by 10 to the negative 7? I don't remember. We can look back at the footage, right? It's all recorded here. So rewind the tape back. Did we get this? I'm pretty sure we did. I think we got 1.8 volts. I do remember that. The current in the resistor is 1.4, the current in the wire, 1.2. So the resistor of X is 1.5, or the total resistance of the circuit, or 5 over 1.6 minus the 2. And so if we took a moment here to, how did they calculate all of this? I think we used this approach, right? We were using Kirchoff's first law to figure out, how much current would be going through, and then kind of applying Ohm's law. We already knew that the voltage was 1.8, so this is how we did it. Here they're doing the total resistance. Okay, so 5, remember, was the EMF over, where's the 1 point? Okay, that was the current. So V over I, and they're subtracting away the 2 ohms of internal resistance. I'd have to think about this for a bit longer to sort of show why this way works. But the way that we solve it certainly is valid. So again, you get sort of the same. I think here they're using the actual resistor equation, right? So saying 1 over the circuit resistance equals to 1 over R1 plus 1 over Rx. So here they've calculated the total circuit resistance, and then they're using the equation for summing, resistors in parallel, summing the reciprocals, and they've solved it for X there. So they've solved for that unknown. But you can see that, in my opinion, this way is a bit more clear, straightforward. It's good to see how both ways work though. And then indeed, half a meter was the length, 1.5 over 3, or if I guess plugged it back into the resistivity equation and solved it for L, which again, if you know the resistance per unit length, this way is much more straightforward than just like use all of the tough values, the scientific notation values that are required when you use the resistivity equation. But you can see you can solve for any subject, including L, and that's what they've done here. They just reorganized the equation that you see up in this box, right? And they've solved it for L. By this time, we know, we've already calculated the area, the resistivity we know from here. So the risk is if you made a mistake with this, you're substituting it back in here, but you would perhaps get an error carried forward, right? Where we're not going to keep penalizing you for the mistake you made early on. And this has been another worked example with Dr. Schleich. We'll see you next time.